All right. So any questions on that? Any questions on anything? Quizzes, assignments, blah, 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 blah. I'd be happy to go over things. If not, then we can get right back into the nitty-gritty of linear regression. I'm hoping that we can get to multivariate regression today, but maybe not. Oh, currently, this is set to be due not this coming Friday, but the next Friday. Schedule. I don't think I've got that set up. But this class meets Monday, Wednesday, Friday, 9 to 9:50. How much material do we have left before we should be able to work on this? After today, you should be able to do part 1 easily. Or multivariate. Wednesday at the very latest for part 1. And then very soon after that, Friday for part 2. Depending on how fast we go. So when submitting code from Jupyter Notebooks, do we have to export it as a .py, or can we leave it as notebooks? You can leave it as a notebook. I can run those just fine. If you have any remaining questions, put them in the chat. Now, in the interest of speed, I'm going to get going. Because, yeah, I would like you to be able to work on this assignment as fast as possible. So let's get there. Okay. So last time we went over the high-level process of linear regression using gradient descent, which is pretty straightforward. So the steps, there are really only 2 of them. So the first one, we start with some random assignment of theta values. With random theta values. 2, no, that's step 1. And step 2 is you update them according to the partial derivatives of the loss function with respect to each theta value. So update each theta using, well, we can do it this way, as follows. So that's theta j equals theta j minus alpha times the partial derivative with respect to theta j of the loss function for each, actually, no, that's right, for each theta j. Boom. And so we talked about some of the other things that go along with this. We talked about why it's important to choose a good alpha value, because it's possible that you might diverge if your alpha is too high, and divergence is when you overstep and your error actually increases from time step to time step, and it just spirals off into infinity. One other thing that you can do, when do I actually talk about this? I want to not get ahead of myself. Oh, there it is. Okay, so we won't do that just yet. But yeah, but now we have the big question, the thing that we didn't go over. Yeah, infinite error is not great. At least it will spiral off into infinity if you let it go that long. But what we hadn't done yet is we hadn't exactly figured out what this partial derivative looks like. Make sure here. Yeah, okay. And so that's what we're going to do right now. Calculate this out. And I'm going to skip a bunch of steps and kind of end up just at the end, but it's a fairly straightforward application of power and chain rule to get where we want to go. But let's somewhat follow the steps. So what is the partial derivative with respect to theta j of our loss function? So, first off, remember what our loss function actually is. 1 over 2m times the sum of I equals 1 to m of the mean squared error. So our predicted value, h, with parameters theta, minus y squared. And this is averaged across your entire data set. Is this loss? You bet it's loss. I think someone makes that joke every single time. And I love it every single time. So this is our loss function. We can sub in for our hypothesis. We know how to calculate this. It's just the linear model that we've been talking about. So, sum I equals 1 to m theta 0 plus theta 1 times xi minus yi. And remember, this is the univariate case. We only have one input. This subscript I refers to the ith example in our data set. So this is what we're calculating the partial derivative of. So after applying power rule and chain rule, we end up with the following two equations that are highly related to each other. So for j equals 0, so the 0th feature, this is our, well, you can think of it as a bias term. I'll explain that in a second. This is the, if you're thinking of things in the y equals mx plus b sense, this is the b term, theta 0. So the partial derivative with respect to theta 0 of j is going to equal 1 over m. See, that 2 went away. I equals 1 to m. It's simply your prediction, xi, minus expected. Boom. That's it. That's your partial derivative. Average over your entire data set. So this is, you can think of it as the average raw error. Since the exponent is gone, this order matters. Predicted minus expected. For j equals 1, it's only slightly more complicated. So with respect to theta 1, j. Still 1 over m. Sum I equals 1 to m h theta xi minus yi times xi. Does this make sense to everybody? So your partial derivative is just the average, well, so you take your raw, for theta 1, you take your raw error multiplied by your original x sub I value, the original input feature, and then you average those over the entire data set. Show j equals n. Ah. Don't you, so if you wanted to do j equals n, you could do that. I was going to talk about this later, but this works, because we're only doing the univariate case right now. The implication of this is that extending it to the multivariate case is incredibly simple, but, you know, somebody asks, so let's do it. 1 over m, I equals 1 to m. Still your prediction, minus expected, times x n. Is that, hold on. There, we'll do it this way. The notation gets a little weird, but pretend this is the nth feature value of xi. There you go. So that's j equals n. When you say expected y sub I, do you mean expected equals actual? Right. Yeah, yeah. So it's the actual one that you get in your training set. It is part of your training example. I sometimes will refer to that as the expected class label because that's what's, again, that's what we expect to see. That's what we want to see. So yeah, the training class value. Now, one thing to keep, so, like, again, and I'll talk about this more later, but the extension into n to multivariate is a trivial extension. You always multiply by whatever your input is here. In fact, you can even think of the j equals 0 case as another extension of this. If we assume the existence of an x0, or sorry, of an x0 that equals 1. This will all make more sense in a second. But before we get going, because I have an example that I want to go through, does anyone have any questions? Something else that I want to write down. So the update equations. Every time, so, what is 1 over m? So 1 over m. M here is the number of examples in your training set. So if you have 100 examples in your training set, you would multiply this sum by 1 over 100. This is just the way of saying that you average this error over, or you average, yeah, this like raw error over your entire data set. That's all that's going on there. All right. This is, with this being the partial derivative, our update equations now become a lot more concrete. So every time, after you make your initial guesses for theta 1 and theta 0, so after guessing, or just randomly assigning theta 0 and theta 1, update as follows. Theta 0 equals theta 0 minus alpha times 1 over m sum I equals 1 to m h theta xi minus yi. And theta 1 is going to equal theta 1 minus alpha 1 over m sum I equals 1 to m h theta xi minus yi times xi. Gradient descent. That's it. So a few notes about this. First off, so some notes. One, make sure that you update theta 0 and theta 1 at the same time. Sure you update theta 0 and theta 1 at the same time. Now, what do I mean by that? Well, I'll get there. Let's see. How do you get the optimal value of alpha? Do we need to change this every time as well? You don't have to. But, so, one thing you can do is just select a bunch and pick which one performs the best. That's honestly typically what I do. I don't spend a lot of time stressing over alpha. I'll try something, and usually if it's bad, it'll diverge right away. But generally, smaller is safer, but slower. You can also use an adaptive alpha rate, which is something we'll talk about later. And in fact, if you're somewhat familiar with some of the machine learning methods out there, or the optimizers out there, The atom optimizer, which is incredibly popular, is an optimizer that has an adaptive alpha rate. But we'll talk about that. So number one, make sure you update theta 0 and theta 1 at the same time. So what do I mean by that? Well, if you, like, let's say, like, obviously you can't do them at exactly the same time because, yay, code is going one step at a time. But let's say that you, first you update theta 0. And so you have your old, you do that, and now you have this new shiny theta 0 value. When it comes time to calculate or update theta 1, right here, you're going to have to use a theta 0 to calculate your output. Make sure that you use old theta values here. So even though you've already updated theta 0 and you have a nice shiny new theta 0 value, don't use it to update theta 1. Just don't. You have to remain consistent in what you're using to calculate your output, or else everything goes to hell. So calculate all losses before updating. That's one way to do it. One way is you could just calculate every single, like, this loss value here for every single theta value before you actually apply the update. That's perfectly fine. What I do is I keep track of my old theta values and I make a copy of the list where I keep all of these things. And so as I calculate new theta values, I put them in the new theta list, and then I make all of my, I calculate all of my outputs using the old theta list. There are a lot of different ways to do it, but just make sure that you don't use new values to update old values. Or new theta values in the updating of old theta values. Don't do that. Okay. Alright. So, an example. With this, we can now actually, like, run through the entirety of gradient descent. Now, bam, there it is. Now we're going to do this. So, we've been here before, but now we're actually going to run through an example of gradient descent. So we're going to assume that we have these four examples. We have one input value, which is size in feet, and our output that we're trying to predict is the cost of a house that has this square footage. So just a reminder, so our updates, theta 0, theta 1, theta 0 minus alpha 1 over m, sum I equals 1. Just so everybody doesn't forget, I will write this a million times. Minus yi, and theta 1 minus alpha 1 over m, I equals 1 to m, h theta, times xi. For this example, will you have the following starting values, and I just picked these kind of randomly. Theta 0 is going to equal 20, and theta 1 is going to equal 0.25. Sure. Normally, how I select starting values is I just choose them randomly within a range. So I think for this assignment, I kind of tried a bunch. Usually just I uniformly picked between like -1 and 1 or something like that. One of the downsides of gradient descent is that your performance has a lot to do with what these starting values are. Because if your loss function is not convex, that's going to determine your starting position. And if you choose a bad starting position, you could end up caught in a local minimum. So that's why I try a bunch of different things, and generally just keep whatever works the best. There are ways around this, but we kind of stick to the simpler stuff here in this class. If ever I get to make that Machine Learning 2 class, we would definitely go over momentum functions and things like that there. But anyway, wishful thinking. We also need to pick our alpha value. I'm going to use 0.1. For the assignment, it is not uncommon to have to use very, very small alpha values, especially if you don't do any pre-processing on your data. I think I've got it set up. I've curated the data in such a way that you don't need to go ridiculously small, but your learning rates might be on the order of, 0.0001 or smaller. In general, it's easy to tell, though, if your alpha is too big. If you diverge, it's too big. Make it smaller. Okay. So step 1 is already done. Look at that. We've got an initial starting theta value. A guess for our thetas, theta 0 and theta 1. So next, let's compute our loss, kind of. Our loss insofar as we need it to update. Theta 1 times xi minus yi. So every update that we make is based on this sum of our predicted value minus our expected value, minus the actual value. So let's calculate that. Remember, our hypothesis is just a linear combination of inputs to outputs plus our theta 0, y equals mx plus b. And what we're going to do here is we're going to average this kind of like pseudo loss, this raw loss, over all, in this case, 4 of our examples. Make sure this works. What am I doing here? Okay, yeah. So this is going to be, for example 1, 20 plus 0.25, because that's my theta 1, times 2104, my input value for the first one, minus 460. That was my expected value. So this is, hey, my example 1 stuff. Example 1. Plus 20 plus 0.25 times 1416 minus 232. So 1416 is our input for the second example, and 232 is our expected or actual output. So we'll just go ahead and mark this example 2. Plus 20 plus 0.25 times 1534 minus 315. Example 3 plus 20 plus 0.25 times 852 minus 178. Example 4. So there's the full thing, that full sum. So this is going to equal 86 plus 142 plus 88.5 plus 55. Now, it might be beneficial to store these intermediate values, just because they will be useful later. Because remember, when it comes time to calculate the update for theta 1, we need to multiply each of these by our raw input. So we're going to just keep an eye on these for now. However, for theta 0, we don't need this, so we average all of these together. Where was I? Yes, there we go. So that's going to equal 371.5. If we divide that by 4, so this is our m in this case, we end up with 92.875. Everyone with me so far? I hope so. And if you're not, just let me know. I'd be more than happy to go back through anything. So we can use this to immediately update theta 0. Great. Theta 0 is going to equal 20, the original value, the original guess, minus 1 over 10, our alpha value, times, make sure, yep, 92.875. So if we calculate this out, we end up with 20 minus 9.2875, which is going to equal 10.7125. So this is our new theta 0 value. New theta 0. Is that the percentage of error? So we are 92% incorrect with these theta values. No, that is not the percentage of error. Because, well, it's not a percentage. This is actually the raw, you can think